Hey everyone, welcome to the first session for Crypto 2025. Our first speaker in the session is William Wong, who's going to tell us about accumulation for Reed-Solomon codes.
Cool, thanks. By the way, so I did give a version of this talk at the Simon's workshop over the summer. So just apologies in advance, there's going to be a lot of the same material covered. Okay. Yeah, let's just get started. I want to start by sort of motivating the problem we're trying to solve. So let's say I want to prove the execution of some program. And the way I'm going to represent this computation is a CPU circuit, which I call F, and some state. So there's some initial state, state 0, and I can model the execution of this program as sort of just repeatedly applying this function F to the state. In full generality, we can also consider like a non-deterministic function, but for simplicity, let's just assume that F is deterministic. Okay. So one thing I could do if I wanted to prove this computation was, okay, I'm just going to use my standard proof system, and this does work, but there are a few issues. So first of all, the solution might not necessarily be memory efficient in the sense that sort of the memory that I need to execute this program is just proportional to the size of an individual state. But for most generic proof systems, proving typically requires space which is sort of proportional to the entire history of the computation. Okay, and so there's some sort of blow up here that we might not necessarily want. Okay, the second issue is that the solution might not be incremental. And what I mean by this is that, let's say I sort of execute 4 steps of this computation, I generate a proof, and later on I want to do another step and then generate a proof for this 5th state of the computation. Well, again, if all I have is this generic proof system, then the best thing I can do is sort of reprove everything that I've done before. And again, this might not be desirable. You could imagine a solution where sort of the proving additional steps only requires cost which is proportional to the additional steps that you want to prove. Okay. So there's a very nice solution for this sort of problem. It's known as incrementally verifiable computation. So IVC is a proof system. There's a prover and verifier. And the idea is that, okay, given some initial state, I can always run the prover to compute the next state, as well as some accompanying proof, which I call the IVC proof, which certifies this state. And I can rerun the prover on this new state to generate the following state, along with a new IVC proof, which attests to the validity of this new state. And I can do this in sort of unbounded number of times. And at any point in time, I can actually just run the IVC verifier on the current state along with its proof to verify its correctness. So the key efficiency property here is that sort of the cost of the prover and the cost of the verifier are only proportional to a single step of the computation rather than the full history. Okay. And I should also mention that there's this generalization of IVC. It's called proof carrying data, which basically, if you imagine IVC as proving a line computation, PCD sort of proves a graph computation, or like a tree. And this is useful in settings where there's sort of more distributed computations. Okay, so it turns out that IVC has a ton of applications. One thing I want to highlight is that actually, in terms of the most performant general purpose proof systems that we have today, they actually all crucially rely on IVC, even to just support proving like just a normal circuit. And so it turns out that sort of improving IVC can actually just improve the performance of actual just normal proof systems as well, in addition to its other applications. Okay. Cool. So I want to talk about building IVC now. And so the first thing I want to do is just briefly cover SNARGs, or succinct non-interactive arguments. So a SNARG is a proof system where we're trying to verify membership in some relation. And well, the prover is going to get the instance and the witness, the verifier is going to get the instance, and the prover is just going to send a proof attesting to the instance's membership in the linkage. Okay, and the verifier is just going to output a 0 or 1. So the two key properties of a SNARG, and one other thing is that we would like this proof to be extremely small, much smaller than the length of the witness, and we would like the verifier's runtime to be also much smaller than the length of the witness. Okay, so the two key properties that a SNARG has is completeness So if I supply the prover with a valid instance and witness, then the verifier is guaranteed to output 1. And soundness is, if this instance is not in the language, then with high probability, the verifier is going to output 0 and reject. Okay, and in general, we actually care about stronger notions of soundness, especially for IVC, such as knowledge soundness, but in this talk, I'm not going to talk about this. Cool. So let's look at how to build IVC from snarks. This is sort of the classical approach. So let's say I have the IVC prover and I increment the state with 1 step. What I'm going to do is I'm going to run the argument prover to generate the proof for this new state. And this proof is going to prove not only that this step function was computed correctly, but also that the previous proof was computed correctly. Okay. And the way I'm going to do this is just by encoding the verifier as part of the circuit and proving that the verifier would have accepted on some hypothetical previous proof. Okay. And this technique is known as recursive proof composition, where sort of you can represent the verifier algorithm and start proving statements about it itself. Okay. And so this works, but there are 2 concrete issues when it comes to actually deploying IVC. First is that even though the succinct argument is efficient, they actually tend to be quite expensive in practice. So for example, the prover might not be as fast as you want it to be, and the verifier might be not be as small as you want it to be, so that when you represent it in a circuit, it actually takes up like a large number of gates. Okay, so we're going to try to improve this, and we're going to do so by using accumulation schemes. So first, let me introduce a reduction. So reduction is, again, a proof system. But in this case, our goal is not necessarily to verify membership in a relation, but rather it's just to reduce membership from one relation into a second relation. So here I start off with some claim about the instance X and the witness W, and I want to reduce this into some new claim about some new instance X prime and new witness W prime. And completeness and soundness are sort of analogous to the case in like a succinct argument. If the original instance and witness were in the relation, then the new instance and witness will be in the new relation. And for soundness, if the old instance were not in the language, then with high probability, then the new instance will not be in the new language. So this is sort of a generalization of arguments. Okay, so with that out of the way, it's actually quite easy to describe an accumulation scheme. An accumulation scheme for some relation R is just a very specific kind of reduction, which turns out to be very useful. It's a reduction from this sort of product relation between R and some other relation R star into R star. Now what is R star? It sort of can be whatever you want it to be, so long as sort of your reduction obeys this, this description. Okay, here I've sort of just like unwrapped the definition. You don't have to look too hard at it. And then here's intuitively how you might use an accumulation scheme. Basically, what an accumulation scheme allows you to do is to take multiple membership claims of R and sort of repeatedly compress it into a single membership claim in R star by just applying the accumulation scheme multiple times. Okay. So why accumulate? Well, it turns out that accumulation schemes can also be used to construct IVC, and actually looks very similar, at least syntactically, between from the construction for succinct arguments. And the only difference is that instead of running the argument prover, we're now going to be running the accumulation prover. And instead of proving statements about the argument verifier, we're going to be proving statements about the accumulation verifier. And the hope is that, well, maybe we can construct accumulation provers which are faster than argument provers, and maybe we can construct accumulation verifiers which are smaller than argument verifiers. And in that case, we would get a more efficient IVC. Okay, so in this paper, we're interested in constructing hash-based accumulation schemes. And to do this, we're going to sort of follow this, I guess by now, classical approach to constructing hash-based succinct arguments. And that is, we start off with some information theoretic proof system. For hash-based arguments, it's an interactive oracle proof. And there's this standard procedure for compiling an interactive oracle proof into a succinct argument by way of Merkle trees. And then if you want to make it non-interactive, you can just apply the Fiat-Shamir transformation. Okay, so what is an interactive oracle proof? It's just an interactive proof where the prover is allowed to actually send really long messages, and the verifier, instead of fully reading this message, can read individual symbols. It has query access to the prover's messages. And you can compile this by essentially replacing the long messages that the prover sends with Merkle commitments, and that gets you a succinct argument. So let's say our goal is to build a succinct reduction. What we're going to do is we're going to define this new information theoretic object, an interactive oracle reduction, which is sort of the reduction analog of an interactive oracle proof. We can compile it into a succinct reduction, essentially using the same compilation technique. And then if we want to make it non-interactive, we can again apply Fiat-Shamir. Okay, so in the rest of the talk, I want to focus on this interactive oracle reduction with the understanding that sort of we can get to our final product in accumulation scheme by way of standard techniques. Okay, so in this work, we sort of precisely define interactive oracle reductions so that they sort of can compile into standalone reductions. So IORs have been considered in some form in the past, sort of as just like modular building blocks for building IOPs. But here we sort of give a definition that is a standalone for IORs. Okay, so in an IOR, the idea is that, okay, now the instance Y will actually be a long message, and the verifier is not actually going to fully read this instance. Instead, it has query access to its individual symbols. You can think of X here as just sort of parameterizing the relation. It's not so important. And the prover and verifier are going to exchange messages. Again, the prover is allowed to send really long messages that the verifier doesn't have to fully read. And the verifier can query individual symbols, and then it's just going to output some new membership claim in some new relation. Okay, and crucially, the verifier can output new instances, Y prime, which are just selected from the long messages that the prover has sent without fully reading them in. Okay, and completeness and soundness, again, are sort of analogous to the case for just normal reductions. The only difference here is that we're actually going to consider this sort of soundness with respect to proximity of the instance. So informally, basically what I'm saying is that an IOR is sound if for any instance which is sufficiently far from the original language, then with high probability, the new instance output by the verifier is also going to be just as far from the new language. Okay. Cool. So let's talk about ARC. So ARC is an accumulation scheme for R1CS, as well as more general constraint systems that I'm not going to cover. Here's R1CS, you don't have to look at it. And here is sort of the cost profile of ARC. The main thing I want to highlight is sort of the verifier's cost, and in particular, it's the number of random oracle queries that it makes. So why is this important? Well, if you recall, sort of what we do with the verifier is represent it as a circuit, and it turns out that in this form, sort of the number of random oracle queries it makes, this corresponds with hash functions in the real world, sort of dominates the verifier's costs, because hash functions are typically pretty expensive to represent in circuit. And so here you can see that the verifier makes a number of random oracle queries that's actually strictly logarithmic in the length of the witness. And this stems from the fact that the underlying IOR from which we compile into ARC actually has a query complexity that's independent of the witness length. Okay, and sort of this query complexity is not actually known for any, at least practically efficient IOPs. And therefore we get an accumulation scheme whose verifier cost is has not been attained by, again, practical succinct arguments. And I want to emphasize that sort of there's nothing fancy going on technique-wise. Sort of the main reason why we can get this reduction is simply because instead of trying to build a succinct argument, we sort of relaxed our goal into constructing an accumulation scheme, which turns out to be easy to make. Okay, and there's some other interesting complexities, but I don't want to talk about it too much. Okay. So let me just try to give a very high-level description of what's going on in the underlying IOR in the rest of this talk. So let's say I have a linear code, and I want to verify that two vectors, f and g, are in this code. Okay. So actually, I don't want to fully verify that they're in the code, but I actually just want to reduce it into one claim that a single vector is in the code. So what can the verifier do? Well, the natural approach would be to take a random linear combination of these two vectors. And so the verifier will just say, okay, instead of testing whether or not these two vectors are in the code, I'm just going to test that this random combination is in the code. Okay, and completeness and soundness sort of follow from linearity of the code, as well as this proximity gap of the code, which I won't go into. The main issue with this description, as I've currently written it, is that it doesn't actually solve the problem. Why? Well, this random combination cannot actually be computed by the verifier, right? And if the verifier actually wanted to compute this combination itself, then it would require iterating through every entry of the vector, which it doesn't have time for. And if instead it wants to just output both vectors and claim that some random linear combination defined by the two vectors as well as the coefficient is in the code, well, you sort of like changed what your claim is. Instead of, it's still a claim about two vectors, now it's just a claim about their combination. So you haven't actually sort of compressed the claim that you're trying to make. Okay. So what we do in ARC instead is, well, first of all, it's a solution that's specific to Reed-Solomon codes. And the idea is that we're going to have the prover recommit to this random combination with a new vector. And the verifier now just needs to test consistency between this new combination and what it thinks the old combination should be. Okay, it's just going to do this by computing what the expected value should be. And instead of outputting the claim that this new commitment is in the code, it's going to actually assert that this quotient of this new vector is in the code. So what is this quotient? I don't have time to go into it, but essentially this is like this tool that has been around for a while. It's been used in other Reed-Solomon proximity tests, and it basically allows us to show that if f and g were far from the code, then with high probability the quotient of this new combination will be far from the code as well. So one thing I want to highlight is sort of that we're using quotients in a different way from prior work. Whereas in prior work, oftentimes when you recommit to like your Reed-Solomon code word, you're actually doing so over a different code, like a different evaluation domain. Here, we're only interested in recommitting it over the exact same code. Okay, and this might not make a lot of sense for those of you who are familiar with proximity tests, because usually you just use quotients to switch to like a better code, perhaps one with lower rate. But for us, we're only interested in this fact that by using this quotient, we can sort of compress like these two claims into a single claim about a single vector. Now, this is very important for an accumulation scheme. Okay.
You have 3.5 minutes.
Oh yeah, and that's all I was going to say. Just to recap, ARC is an accumulation scheme. We construct it by building an IOR and then compiling it into an accumulation scheme. And this enables highly efficient IVC and PCD. Thanks.
Thank you. Are there any questions? Okay, I had a quick question.
Sure.
So you said accumulation schemes are already known, right? But they're not hash-based. Can you maybe explain a little bit about what kind of assumptions they require?
Oh yeah, sure. So using these group-based assumptions, so like discrete logarithm-based, and so I guess.
Audience. Okay, let's thank William.
Forward, backward, laser.
17 minutes?
Sorry.
17 minutes.
Yeah. Okay, our next talk is on breaking verifiable delay functions in the random oracle model, and Z, go on.
Okay, test.
Yeah.
I think there's.
One,
there's
two.
still,
Yeah.
it's fine. So, okay, great. Yeah. Okay, should I start? Okay, I'll start. So hello everyone, I'm Z. Today I'm going to talk about verifiable delay functions in the random oracle model. This is joint work with Arthur and Wei-Chang. So there's a joke here in case you missed it. Okay, so it doesn't work. No, it doesn't work. Okay. Okay, great. So I'll start with introducing the random oracle model. It's simply a set of distributions indexed by natural numbers. And each OL here is just a uniform distribution over all binary functions of output length L. And we say that an algorithm A is in the random oracle model if it has oracle access to the random oracle, meaning that it can submit a query Q, an arbitrary binary string, and get a uniformly sampled answer by the distribution. And then verifiable delay function in the random oracle model contains a tuple of algorithms, eval and verify, where each of them have oracle access to the random oracle. And eval takes an input X in the set of input space and map it to something in the output space Y. And then it sends the output Y and a corresponding proof string pi to the verify function. And then the verify decides whether to accept or reject. And as the name suggested, VDF has three requirements in terms of the security and efficiency. So the first one is that it needs to be verifiable in the sense that the correctness of the output given by the eval function can be efficiently and publicly verified. So more concretely, if eval function makes T queries to the random oracle, this is like consistent with how we measure efficiency in the random oracle model. We count the number of queries the algorithm make to the random oracle. So if eval makes T queries, then we require verify to make S queries where S is way less than T. So maybe even in the order of polylog. And then we also require the delay, which is saying that if eval can be computed in T queries to the random oracle, then if I make little of T queries, there's no way I can compute eval, even if I allow parallelism. And in the random oracle model, parallelism just means that I can submit in one round a bunch of non-adaptive queries. And here the requirement is saying that even if I allow little of T of non-adaptive round of queries, I still cannot compute eval. And lastly, we want VDF to be a function, meaning that for one given input, we have one unique output. So that's VDF. And since its introduction, VDF has had a lot of applications. One of the very important one is in the construction of randomness beacon, which is ideal services that publish randomness regularly. And moreover, the randomness cannot be predicted or manipulated. And the common recipe to construct randomness beacon is through some public source of randomness, for example, the stock prices, and then run a randomness extractor to extract a random seed and apply a pseudorandom generator on top of the seed. But the issue of this construction is that because randomness extractor and pseudorandom generator, they're both efficiently computable, and also stock prices is known to be easily manipulatable. So the final randomness can be biased. So the solution here is to apply a VDF on top of the random seed. And because of the delay requirement, we know that the final random strain cannot be computed before the stock market closes, and therefore it cannot be manipulated towards anyone's favor. And uniqueness tells us that there is no ambiguity in the output. Okay. Another notable application of VDF is in blockchain, and in particular in the construction of the leader election algorithm. And again, from uniqueness, we know that each time we have one unique leader, and delay ensures that before the predetermined announcement time, no one's able to know the leader beforehand. And this is actually being deployed in practice. Okay. So in this paper, what we show is that verifiable delay functions do not exist in the random oracle model. That's our main theorem and only theorem. It's very easy to state and easy to remember. Okay, and now you might ask, but we know that VDFs, they do exist in the standard model, right? They're constructions. And why do we care about random oracle model? It's not real anyway. We cannot instantiate it. Why do we care? But it turns out to be that, at least my personal opinion, and I hope to convince you that studying cryptographic primitives in the random oracle model can help us answer a lot of important questions. So for example, now I tell you VDF is important, has tons of applications. So then what's the first question you want to ask me? You want to ask me how do I construct it? But then it's a crypto primitive. Then therefore we ask what crypto is needed to construct VDFs, right? So we also know that all the existing VDF constructions, they rely on algebraic assumptions, and none of them are post-quantum secure. And on the other hand, our result, the impossibility of VDF in the random oracle model, tells us that VDFs cannot be constructed in a black box way from very light crypto assumptions, such as one-way functions, one-way permutations, collision-resistant hash functions, and all sorts of hash functions. And this is telling us that to construct VDF, even the classical one, not the post-quantum secure one, you still have to start from something higher in the hierarchy than hash functions. And moreover, to get post-quantum secure VDF, you have to start with much more complex assumptions, such as lattice-based ones. And the second question I want to ask is, okay, we have VDF constructions. They're based on whatever constructions, assumptions we have. But what security do they have? And we also know that standard model constructions based on standard model assumptions, they do not give you concrete security analysis. And in other words, we don't know, once we deploy the scheme, we don't know how to set security parameter, because there's no concrete relationship between how many bits of security you want and what is the security parameter, if you start with standard model assumptions. Okay, so the way to get around with that, but now you might ask that, yeah, we proved that VDF do not exist in the random oracle model. So why are you telling me this? Are we hopeless? How do we know the security? But another primitive that William just mentioned kind of is at a very similar situation, incrementally verifiable computation. IVC is conjectured and also even partially proven to not exist in the random oracle model. And yet it's deployed everywhere in blockchain-related applications. So how did people handle this? So one way to study its security is to consider alternative idealized models, such as the low-degree random oracle model, which is simply the low-degree extension of the random oracle model, or a arithmetized random oracle model, which is random oracle plus some arithmetization oracle. And an alternative is people also studied some relaxation of IVC in the random oracle model to get around the impossibility result just for security analysis purpose. So there are a lot of ways to get around with this kind of random oracle impossibility, but our result kind of suggests that maybe we have to adapt similar approaches for VDFs. Okay, so hopefully by now I've convinced you that the result is interesting and it's useful. I want to spend the rest of the talk to give a little bit of intuition on how we prove the main result. So before getting into that, I want to introduce some new terms, query complexity and certificate complexity. And those objects or complexity measures have been studied in complexity theory for the past few decades. And it also is the initial inspiration on how we prove our final result. So what are those? So first, when talking about query complexity and certificate complexity, we need to talk about Boolean functions. In particular, in this case, for simplicity, we consider Boolean decision problems. Function g that takes an n-bit input and give me a decision bit 0 or 1. And as an example, we can consider this 3 Hamming weight problem, where it takes input a and it outputs 1 if and only if the Hamming weight of a is at least 3. That's a very concrete problem, and it's one instantiation of G. And query complexity, D of G, is just the minimum number of bits in A I need to read to compute G. So again, as an example for this 3 Hamming weight problem, I claim that the query complexity is N, because for any deterministic algorithm, there always exists a worst case input A so that I have to read the entire string. So for example, if I say that now my algorithm is just to read until it finds three ones in the string, but then what if I give you a string where the first n minus 3 bits are 0 and the last 3 bits are 1? So here, in this case, query complexity for this function is n. Okay, and then I want to define the certificate complexity, which there are like a lot of formulas, but C of G is simply the max of C0 and C1, where C1 is the certificate complexity for the function evaluating to 1, meaning that the minimum number of bits in the input I need to provide to prove that given this input, G evaluates to 1. And similarly, C0 is defined to be the minimum number of bits I need to provide to prove that G of A is equal to 0. And in the case for this 3 Hamming weight problem, I claim that C1 of it is equal to 3, because I want to tell you that give me an input A. I want to tell you that the function evaluates A to 1, meaning that I only need to give you 3 bits that 3 locations in A that has 1. And on the other hand, the 0 certificate of 3 Hamming weight is n minus 3, because given any input to prove that this function evaluates to 0, I need to give you at least n minus 3 bits. And it is almost trivial to see that certificate complexity is a lower bound on the query complexity. But it is proven for, I think, like 20 years ago or like 3 decades ago that actually the square of the certificate complexity is an upper bound on the query complexity. So that's known. And now you might ask, why am I talking about this? Why is it related to VDF? And now I claim that using this framework, we can remove delay in VDF, meaning that for any construction you give me, there is no way that we can satisfy the delay requirement. So why is that? So recall that this is the framework of VDF. Here, for simplicity, I omit the proof string sent by eval, but we can add it. We added it in the actual paper. And now I set this Boolean function g into eval. And here I want to do some pattern matching, because in the VDF language, eval knows x, but it has oracle access to f. And what I actually care about is delay requirement care about what is the number of queries eval needs to make to evaluate this function. So here, to do this language translation, I set eval x to be the eval function with input x hard-coded and input the random oracle f and measure the number of queries eval function makes to the random oracle. And now with this translation, I claim that the certificate complexity of this function, this new eval function, is the number of queries made by the verifier to the random oracle, by the correctness and uniqueness of the VDF. Correctness tells me that one y is going to be accepted, and uniqueness tells me that any y that's not computed by eval will not be accepted. So S is the certificate complexity that I have for this eval function. And then magically, using this relationship that's being established before, we know that there exists an algorithm with at most S² queries that compute eval, meaning that we break the delay requirement of VDF. And of course, there is one caveat that I didn't have time to explain, which is VDF, as any other crypto primitive, has cryptographic correctness, meaning that the correctness holds only against bounded query adversaries. But here in complexity theory, people study perfect correctness and statistical correctness. There is no bounded adversary. So we have to handle this in the paper. Okay, then just to recap, in this paper, we show that one cannot construct verifiable delay functions in the random oracle model. And in other words, if we kind of look at this table of all the requirements we want, we know that it's impossible to combine uniqueness and delay together. This is our result. But if we relax this in the sense that we only keep verifiability, but we remove delay, remove uniqueness, then we know that this such scheme exists, which is our just simply proof of work. And on the other hand, if we only require delay without uniqueness, so verifiable delay thing, then it also exists, which is a proof of sequential work, which we're familiar with. And this leaves us to one last open problem, which is what if I only require uniqueness, but no delay? Can we construct such a scheme, or can we prove similar impossibility as the VDF? And this can also be formulated as a very interesting open question in query complexity versus certificate complexity in complexity theory. So that's everything I want to talk about. Thank you.
Any questions?
So the technical overview that you described at the level that you described, to me, it seems that your proof is agnostic to the structure of the oracle F, meaning that you can pretty much replace the random oracle F with any other oracle with possibly more structured oracles, and the same arguments should go through. Probably the same arguments do not go through, but can you tell me where you are making use of the fact that you are dealing with an unstructured random oracle F as opposed to some more structured oracles? Because your proofs should not work if we replace F with more structured oracles.
Why shouldn't it work? Like, is there any other oracle model that
For example,
exists?
you can consider an oracle for composite order groups, and probably it should not work because if the assumption is sufficiently strong, we can build verifiable delay functions. So there should exist oracles relative to which
we do kind of require in our proof technique. It's kind of necessary for the oracle function, this F, to be at least efficiently samplable. But I'm not familiar with the Oracle model you just mentioned, so I'm not sure. It shouldn't, if there is construction, then probably that's the place that it would stop working. But I need to look at the specific Oracle you have in mind in more detail to see where it breaks. But it's a great question. Maybe we could make it slightly more general. Yeah.
Okay, sure. Thanks.
Thanks for the talk. If I want to construct a verifiable delay function in the random oracle model, and I'm willing to relax the time it takes to verify the proof. So let's say I want a function that takes time t to compute. I think it should be trivial if I also allow time t to verify.
Yeah.
But I think your lower bound, if I got it correctly, only shows that you cannot verify it in time less than square root of t, right?
Yes.
So is there a construction in the random oracle model where I can get this square root of t verification?
In the paper, we do have a construction that almost matches this bound.
Okay.
Yes, but there is caveat. This bound, this S-square bound, it works only for perfect correctness and statistical correctness, meaning that we always consider unbounded adversaries. But if we consider bounded adversaries, that's the open question that I mentioned at the end. It's in the cryptographic setting, and this S-square query algorithm becomes all of S times T. So in the cryptographic setting, it is still an open problem, and we don't know whether it's tight or not. Yeah.
Thank you. So maybe this is exactly this cryptographic correctness, but like, what about cryptographic uniqueness? Like, I only need to convince. Let's say I only need to convince a verifier that, or like a verifier only needs to reject bad outputs with overwhelming probability, not with probability 1.
Yeah.
Does that like then change the picture? I mean, also, I guess like similarly related to that, the certificates, like for example, a PCP has much lower query complexity, right?
Yeah, so it is related to this cryptographic correctness that I was like handily talking about. So basically, there are like two things that we're assuming in this framework that are perfect. The first one is completeness. The second one is uniqueness. We're assuming that the verifier accepts with probability 1 for whatever eval output. And we're also assuming that in this framework, for any random oracle that we sample, for every random oracle, for every input, the verifier accepts one and only one input. That's the assumption here. But you're right. If we consider the cryptographic setting where we have imperfect completeness and computational uniqueness, then this bound becomes worse in the sense that we have the adversary is going to make S times T queries instead of S squared.
Okay.
Yeah. So in fact, in this setting, in the perfect and statistical setting, we rule out something slightly more than VDF because we don't really need delay function because S squared is polylog in T.
But it's, I mean, okay, I mean that then the result makes more sense to me because the constructions that we have don't have perfect uniqueness.
No,
right? Like
no.
there's a proof there
Right,
and
yeah.
it has a soundness error.
Yeah, exactly. We can handle that. It's just with slightly worse bound. And that is exactly the open question.
Thank you.
Yeah.
Okay, let's thank Z again. Okay, the next talk is by Roman, who will tell us about deniable authentication against malicious verifiers.
Okay, thanks for the introduction. This is a joint work with Rune Fiedler. And I want to start this talk with a story of Alice and Bob. And Alice and Bob were very good friends, maybe even a bit more than just friends. And importantly, they were fully trusting each other. So Alice decided to tell Bob a secret of hers. However, as time passes, Bob became from that nice, trustworthy person, a bad person who was now trying to betray Alice by telling her secret to someone else. In this example, this judge. And this judge is now wondering if he should believe that Alice actually sent this to Bob, or if Bob just made this completely up by himself. And many messaging apps like Signal try to protect Alice in this situation by a property that's called deniable authentication. So deniable authentication means when Alice authenticates a message for Bob, Bob is convinced by the authenticity, but Bob cannot convince someone else that this message is authentic. And one primitive to achieve this are designated verifier signatures. In designated verifier signatures, both our sender Alice and our receiver Bob have a public and a secret key. And Alice generates a signature using her secret key and Bob's public key. But importantly, Bob can also generate a signature that looks like a signature from Alice using his secret key and Alice's public key. And the judge should not be able to distinguish these two signatures. So then the judge won't be convinced if Bob shows him a signature from Alice because Bob could have generated it himself. However, there's a very important catch here, because in this model, we are assuming that Bob generates this public and secret key pair honestly. And this is a security notion that is trying to protect Alice from Bob. So I think we really shouldn't do this. So in the story I told you this would be fine, but what about an alternative version of that story, where Bob was a bad person from the beginning and he was just using this mask to pretend to be a nice guy and trick Alice into telling him this secret? That's the model that's the situation we are studying in our paper. And we have several contributions. The first one is a model for this deniable authentication against malicious verifiers for designated verifier signatures. Then we also consider a very similar setting for key exchange and show that the Signal initial handshake protocols X3DH and PQXDH are not deniable in this model. And this is in contrast to prior works who have claimed that they are, but they relied on a novel assumption called the knowledge of Diffie-Hellman assumption, or the extended version of that, and we show that both of these variants are broken. Then we give a construction of designated verifier signatures in the random oracle model. It's a very simple construction based on NISIX. But shortly after we came up with these constructions, we came up with an impossibility result in the standard model that shows that the security notion is not achievable assuming indistinguishability obfuscation exists with a concrete attack, which in particular means that our random oracle construction is in fact uninstantiatable. And if you would try to replace the random oracle with a concrete hash function, it becomes insecure. Okay, so let me start with the model. So recall this was the model, or the existing model for designated verifier signatures. But if we want to assume that Bob is malicious, we cannot assume that there's a secret key for Bob, because he might generate his public key in such a way that there is no secret key. So we need to replace this with something else. But it should still be a secret that Bob is guaranteed to possess, because, well, if it would be possible to fake the signature without any secret, then clearly the signature would not be unforgeable. So we need some secret that Bob is guaranteed to possess. And in our work, we choose the random coins that Bob uses to generate his public key. So we make no assumption how Bob generates his public key, but the random coins he used for that, they should serve as secret key to fake signatures. However, this model still has a problem. Namely, we're assuming here that Bob is isolated in the sense that everything he comes up with, he has to sample himself. And I want to convince you that this is not realistic by this huge number that I put here on the slides. And this number is the product of two 2048-bit primes. And as far as I know, there's no algorithm that can sample such a number without knowing the primes. However, even though I was the person who put this number here on the slides, I don't know the primes. And I can convince you of this because, well, this is the public key of the iscr.org web server, and I just copied it on the slides. And so, of course, Bob could maybe in some way do the same and use this public key to generate in some convoluted way his own public key. And then our model would assume that he knows the prime factors of this number, which is not realistic at all. So to fix this definition, we have to model everything that Bob might know without generating it himself. And we do this by giving Bob an auxiliary input that contains everything that's independent of the scheme's public parameters. So think of this kind of a copy of the internet if you want. But he can also get some things that depend on the public parameters, like public keys of other verifiers, public keys of senders, valid signatures, and maybe some more things we didn't think about. And these should be given to Bob as input or Oracle access. For the purpose of the talk, you can ignore everything except for the auxiliary input. In the paper, we also show how to deal with public keys of other verifiers. You just have to be careful to avoid some trivial attack where Bob would just copy the public key of someone else. And public keys of senders and valid signatures are relatively easy to add. So to summarize, our definition for malicious source hiding now looks as follows. We say that for every adversary A, this is meant to model Bob, and his job is to generate a public key. There exists an extractor that gets the same inputs as Bob, and in particular the same random tape, and forges signatures, such that for every distinguisher, think of this as the judge, and for every auxiliary input, which is given both to the adversary A and the extractor E, the distinguisher cannot distinguish between real signatures from Alice and fake signatures from the extractor. Now, before I want to describe our solution, I want to start with a few ideas how to construct this that don't work. And I think one natural idea is to use a knowledge type assumption. These are assumptions that guarantee if you generate a certain element, then you could, with your random coins, also generate something else. A famous example of this is this knowledge of exponent assumption. However, most of these, like the knowledge of exponent assumption, are not secure when you add these auxiliary inputs that we need in our model. This was shown in a paper from Stock 2040 by Bitansky, Canetti, Paneth, and Rosen. And the knowledge of Diffie-Hellman assumption that I mentioned in the beginning was actually designed to exactly circumvent this problem, but we show that they fail to do so, and they are actually insecure against very simple auxiliary input, and you don't even need I/O. Then I think another natural idea is to add a proof of knowledge to your public key that proves that you know the secret key. But that also doesn't work, and there are two different explanations depending on how you define knowledge soundness. So the first variant is black box extraction, which means the proof system guarantees that for every algorithm that generates a proof, there exists an extractor that takes as input the proof and a trapdoor to the common reference string to extract a witness. But in our setting, this would lean to a notion where the extractor would need a trapdoor for the common reference string. However, in reality, if your system is set up correctly, no one will know this trapdoor. So it would be very unrealistic to assume that Bob knows it for deniability. So yeah, this doesn't work. Another version to formalize proof of knowledge for NISIX is via white box extraction, which is typically used for snarks. And that guarantees for every algorithm that generates a proof, there exists an extractor that can extract the witness using the same random coins as the adversary that generated the proof. So this would match perfectly to our definition. But unfortunately, again, this impossibility result kicks in that shows that this cannot work when we have this auxiliary input. So our idea for our random oracle construction was to use the construction that's shown here in the middle, so to use a NISIC POC with black box extraction. And our basic idea was, well, if Bob generates the public key, if Bob generates the CRS himself, instead of having a global CRS, then it's realistic to assume that he can know the trapdoor. So naively, what we could do is, well, Bob generates his public key as follows. He first generates a CRS, then generates a key pair for a traditional DVS, and then a proof that he knows the proof of knowledge of the secret key. Now this, of course, doesn't work because we want to assume that Bob is malicious. But we have, and this proof would be useless if the CRS is not generated correctly. So we have to force Bob to generate the CRS randomly. And what we can do is, well, we can generate it via random oracle. Of course, that only works for proof systems that require a random string as CRS. And yeah, so we could do it as follows. Bob just has to call the random oracle on the public parameters of the scheme and something that's unique to him, like an identity, to get the CRS. And the idea is that now the extractor can run this algorithm A internally and program this random oracle query to a CRS where it knows the trapdoor and then extract from the proof. This still doesn't quite work because the adversary could output a different public key when we change this random oracle query. But we can circumvent this with a trick that's very similar to the Fiat-Shamir transform. And that is basically to just include in the hash function also the public key we are trying to prove. So that's our final construction, and that can be proven secure in the random oracle model. So next I want to describe our impossibility result, and it works. The high-level idea is very similar to the work by Bitansky et al. That I mentioned before. And formally it says, well, assuming I/O exists, no DVS can be simultaneously malicious source hiding and unforgeable. And the idea of the proof is that malicious source hiding guarantees us when we have such an algorithm A that inputs the public parameters and outputs a public key, then there is an extractor that gets the same input and can simulate signatures. And in particular, these signatures should verify. Otherwise, they would not be very convincing and very easy to distinguish. And for our impossibility result, we consider an algorithm A that gets as auxiliary input an obfuscated version of this verifier key generation algorithm with a hard-coded PRF key, and it just runs that. And then we can use the punctured programming technique by Sahai and Waters to show that this is indistinguishable to a setting where this obfuscated program has just one specific public key hard-coded inside it. And this indistinguishability guarantees that now everything should be indistinguishable. So in particular, our extractor still has to output signatures that verify with, at least with overwhelming probability on the right-hand side here. But this means this extractor now has to break unforgeability because otherwise, this public key pk star here is just some hard-coded public key. There's no real hint we are giving the extractor here. Okay, so how does this fit together with our random oracle construction? Well, in our random oracle construction, an obfuscated program cannot access the random oracle. And in our random oracle construction, it is impossible to generate a valid verifier public key without access to the random oracle. So that's why this impossibility result doesn't work. However, if you would instantiate the random oracle with a concrete hash function, of course an obfuscated circuit can evaluate it. So the impossibility result applies. So that means our construction is in fact insecure if you instantiate the random oracle, and you should not use it in that way. Okay, so this, I think, leaves interesting directions for future work. And I think the most interesting problem is, of course, to circumvent our impossibility result. And I think there are several possible approaches. The first one would be to consider interactive protocols. I think this should be fairly easy because then you can use an interactive proof of knowledge instead of an ISIC, and then you shouldn't have these problems. However, this might be undesirable for applications like end-to-end encrypted messaging because users might be offline. Another idea would be to restrict the auxiliary input. However, we are convinced that for realistic restrictions, like for example, you could try to restrict it to just auxiliary input that can be sampled efficiently. they are not sufficient to circumvent our impossibility result. And in fact, prior work has proposed schemes that would require publishing in obfuscated circuits as public parameters that is sufficient for our attack. So if you would try to restrict the auxiliary input, you would in particular assume that such a scheme never gets deployed. Well, probably they will never get deployed because they are quite theoretical constructions that use I/O. However, please keep in mind that we need I/O here mostly because our attack is very powerful, because it can break every possible construction for a DVS. But if you look at her concrete schemes, it might be simpler to attack even without I/O. That's, for example, what happens with this X3DH, PQXDH, and knowledge of Diffie-Hellman assumption, as we show in our work. And finally, and I think the most interesting direction is to consider private verification, where a DVS cannot be verified with the public key, but just with the secret key of Bob. In this setting, our impossibility result doesn't work, but we also haven't found a way to construct a scheme in this private verification setting. So yeah, it would be very interesting to resolve this and see if it's possible or not. Finally, I think it's also interesting to study maybe different models for deniability against malicious verifiers that maybe don't rely on the verifier's randomness for simulation of signatures, because this has other drawbacks apart from our impossibility result. For example, it's not meaningful against quantum adversaries because quantum algorithm can prove that they deleted their random coins. And one example I want to mention here are time-deniable signatures. These don't have problems with malicious verifiers, but they need other strong assumptions. Okay, thank you for listening to my talk.
Thanks for the very interesting talk. I have a question about slide number 17, where you start discussing the interactive case. And you said that this interactive proof of knowledge seems to be sufficient. I'm not so sure about it. The reason is that we think usually about the interactive proof as not being transferable. You cannot show them to a judge. But Bob, the malicious Bob, could have chosen his query as a hash function of what had been initially given to him by Alice. And in this case, you are turning the interactive proof into a Fiat-Shamir signature, which can be shown. So I think that unless you are very careful, just using an interactive proof in order for Alice to prove something to Bob in a way that cannot be shown later to a judge will not work, because Bob will just simulate a signature.
Okay, I think on this slide we actually, or I meant something else with interactive proof of knowledge. So I meant that Bob proves in an interactive procedure that he knows his secret key to his public key. And then you run a normal DVS with simulatable.
Okay, but it's not the standard interactive proof of knowledge, which is sufficient.
Yeah.
You have to be more careful. Okay.
Any other questions? Okay, let's thank Roman again.
All right. Yeah, you good? All right, got material there? No, thanks, all right, thank you.
The last talk in this session is by Leo Rotem on straight line knowledge extraction for multi-round protocols.
All right, thank you. Thank you all for coming. Yeah, so this is joint work with Stefano, who's here. And what this talk is about, yeah, it's about transforming interactive arguments of knowledge into non-interactive ones in the random oracle model. So just so that we're all on the same page, what do I mean by interactive arguments of knowledge? Well, we have a prover P and a verifier V. They share some common input X. P additionally has some witness W for X. The two interact, and at the end of the interaction, V either accepts or rejects. So the standard things that we want are completeness. So in an honest interaction, V should accept. Knowledge soundness that we'll define formally later on. So very informally right now, for any efficient P star, if V accepts, then this P star should know a witness. And we'll make this formally in a few slides. And finally, today, we'll only be interested in public coin protocols, which essentially means that all of these challenges or messages are just uniform randomness. So the way you typically do this is using the Fiat-Shamir transform. So we just de-randomize the verifier's challenges using a hash function. So the ith challenge is a hash of the transcript of the interaction so far. And this is great. And this is the canonical way to do this. And in most settings, this is what you should do. And it turns out that we can actually prove that this is secure if you model this hash function H as a random oracle. So this is typically done using the forking lemma, which rewinds the prover multiple times in order to get multiple accepting proofs. And from that, we can extract a witness. So this is great. Unfortunately, in some settings, this rewinding introduces an issue. So one issue is that we end up with non-tight reductions because we want multiple accepting proofs from the prover. It needs to succeed multiple times. And so the success probability of the extractor or the reduction can be much smaller than the success probability of the prover that we started off with. Another caveat is that in some settings, this might not be secure under composition. So either composition with itself or compositions with other protocols. And we do have examples of such settings where using Fiat-Shamir actually becomes insecure. And finally, this is not a caveat per se, but it's worth noting that once you move from 3-round protocols to multi-round protocols, actually analyzing the security of Fiat-Shamir becomes much more cumbersome. And it's only been recently that we actually had proofs of security for Fiat-Shamir for multi-round protocols. So a somewhat more flexible idea or way to construct non-interactive arguments of knowledge from interactive ones is doing so in a way that admits a straight line extractor. So a straight line extractor runs a prover only once. And in the setting that we'll consider today, it typically just extracts the witness by reading it off the queries issued by the prover to the random oracle. We can just look at all of the queries and sort of compute the witness from that. And for signal protocols, so 3-round protocols, it turns out that we do have transforms from interactive arguments of knowledge to non-interactive ones that admit such a straight line extractor. So the first was due to pass, and it's based on some sort of a cut and choose based approach. And it was later on shown to be even secure in a quantum random oracle model by Unruh. And this is a kind of a format mismatch. But the second one is due to Fischli, and a couple of years later, that's proves based on a proof of work type mechanism that we'll see later on. So both of these have tight reductions, even though the proofs that you end up with are longer than if you use Fiat-Shamir. And they're also secure under composition in settings where Fiat-Shamir is not. Good. So this is what we know for signal protocols. But now the question is, what happens with multi-round protocols? Because we do have multi-round protocols that are public coin, that are more than 3 rounds. So for example, identification schemes that require more than 3 rounds, or recursion-based arguments like bulletproofs or folding that we heard about earlier today. So in this latter type of protocols, we recursively reduce the statement size from n to n over k for some parameter k. So we end up with round complexity, which is something like log n over log k. So for like interesting choices of k, this is super constant, and it can go up to log n if k is equal to 2. So the question that we want to ask in this talk is, can we design general transformations in the random oracle model that can be applied to these multi-run protocols, and in addition, admit a straight line abstractor? So this is exactly what we do in this work. We give two such transformations. The first is based on kind of extending Fischlin's idea to multi-run protocols. This has smaller proofs than the second transformation, but it only supports, or at least our analysis only supports bounded run complexity, so up to log lambda over log lambda, where lambda is the security parameter. And the second transformation is based on a cut and choose approach similar to PASS. It has larger proofs, but it supports an arbitrary number of rounds. And in addition, we also have an analysis for that in the quantum random oracle model, following the techniques of Chiesa et al. In kind of similar settings. And as far as we know, this is sort of the first kind of restriction-free proof of security in the quantum random oracle model for a transformation for the class of algorithms or arguments that we consider here. So what I want to do is I want to focus mainly on our first transformation because it's somehow kind of more interesting from a technical perspective. But before we do that, I just want to mention that we're kind of interested in transformations that only assume a random oracle on top of the underlying arguments. So if you are willing to make additional assumptions, computational assumptions, that there are other sort of compilers that compile into non-interactive arguments with straight line extractor, and we have a full account in the paper. Good. So what I want to do in the time that we have left is I want to kind of give some definitions that will help us later on. So we'll define what we mean by special soundness of multi-run protocols, and then we'll give a somewhat more formal definition for knowledge soundness for non-interactive arguments in the random oracle model. Then we'll see our Fischlin-based transformation. This is going to be the heart of the talk, and then we'll conclude. Good. So what do I mean by special soundness for multi-run protocols? Well, for that, I want to introduce a notion of a tree of transcripts. So when N1 through Nr tree of transcripts is a collection of transcripts that can be arranged in a tree of the following form. So all of them share the same first prover message. So that's A1. Then you have distinct N1 challenges and corresponding replies. Then for every of these replies, you have distinct N2 challenges with corresponding replies and so forth. So it's a tree of height R, where the arity of at each level is Ni. Each node corresponds to a prover message. Each edge corresponds to a verifier message, and the neighboring edges are distinct. So special soundness in this case just requires that if I give you such a tree of transcripts that are all accepting, from that you can compute a witness. And in this language, standard special soundness is just 2 special soundness. Good. So now what do I mean by non-interactive arguments in the random oracle model, where now the proof is just one message from the prover to the verifier. Everyone gets access to a random oracle. Completeness is the same as before, but if it's probabilistic, you also take the probability over the choice of random oracle. And special soundness, so I'm going to give a non-adaptive definition, even though everything I say today can be extended to the adaptive setting as well. So there exists an extractor such that for any efficient P star, input X, auxiliary input, and randomness, the following should hold. So if I run P star on X, the auxiliary input, and this randomness, and it outputs a proof pi, well, if this proof is accepting, so if I give the extractor X and the list of all queries issued by the prover to the random oracle, then the extractor should compute a valid witness. So that's the definition that we'll work with. All right. So that's all for definitions, and we're ready to sort of see our Fischlin-based transform. So for that, let me recall or recap the Fischlin transform for sigma protocols. So sigma protocols are just a special case of what we just talked about. There are 3 round protocols. They have these 2 special soundness, or just special soundness, that says that if you have 2 transcripts with the same first message and distinct challenges, you can compute a witness from that. So Fischlin's idea is to use a proof of work-like mechanism that we'll see on the next slide to force a successful prover to query the random oracle on 2 such transcripts, and from that you can compute the witness. So what's the idea? The idea is that let's say that the first message is fixed, the prover has to find a challenge C and the response Z such that it's accepting. And in addition, it hashes to 0. Right? And so the idea here is that if this hash is good, with let's say a random oracle, then a successful prover will have to, with probability 1/2, will have to query the oracle on 2 accepting transcripts that share the same first message. Right? So this is kind of, yeah, and then you just extract using special summons. So, this is not quite true. So first of all, this only happens with probability 1/2. It's also true that with probability 1/2, the first query will be good. And the second issue is that we sort of assume that the first message is fixed, but there's nothing yet stopping the adversary from sort of resampling the first message in each query. So both of these issues are just handled via parallel repetition. So Fish-Lins transforms is the following. The prover has to find lambda transcripts, where lambda is a security parameter, such that all of them are accepting and all of them hash to 0. And we sort of throw in the vector of all first messages inside the hash, and this essentially fixes the first message in all of the repetitions. All right, and this can be shown to be knowledge sound. So now we want to extend this idea to the multi-round setting. So here's an idea that doesn't work, but it will get us closer. So what we can do is we can just use Fish-Lins transform as is and try to apply it to multi-round protocols. So given the first message, what the prover has to do is find the transcript that is accepting, and in addition, it hashes to 0. And then you repeat in parallel to handle the same issues that we talked about before. So this is kind of the failed attempt. A proof consists of lambda transcripts, all of them hash to 0, and all of them are accepted. The problem is that this is not knowledge sound. And the reason why this is not knowledge sound is the following. So what we need to apply this generalized special soundness is a tree that has a certain topology to it. But what Fish-Lins transform only gives us is a bound on the number of leaves of the tree. So for trees of depth 1, which correspond to sigma protocols, this is the same, right? I mean, for trees of depth 1, the number of leaves and the topology are just the same. But for deeper trees, it's no longer the case that the number of leaves kind of determine the topology of the tree. And this introduces sort of an explicit attack on this naive attempt. So to see its attack, let's consider just two special soundness. So what we want in order to extract is a tree that has this form. Unfortunately, what the prover can do is can fix the first 3 messages of the protocol, and then repeatedly sample the last 2 messages until it finds a transcript that hashes to 0. So this is the tree that we actually get, right? And even though the number of leaves might be the same, this is not enough in order to extract a witness. So like the idea to fix the situation will be the following. So first of all, for general special soundness, we might need more leaves. This can be easily fixed by just requiring that the hash hashes to 0 to the L for some parameter L, not necessarily 0. But in addition, and this is kind of the crux of the idea, we'll also limit the number of admissible challenges in each level of the tree. So now P star cannot resample C2 sort of until it finds a hash or a transcript that hashes to 0, because eventually it will run out of challenges that it can resample. All right, so we can present our full transformation now. It will be parameterized by this L and also integers K1 through KR, so 1 for each round. And the successful proof will be, again, lambda transcripts, such that, as before, they all hash to 0 to the L, and they are accepting. But in addition, we also require that the jth challenge in all of these transcripts is bounded by this parameter Kj. All right. So the main insight here is that even though the number of leaves for deep trees doesn't determine the topology, if you sort of bound the arity, it tells you a lot more about the topology. So now we have kind of a balancing act, right? On the one hand, a malicious prover, P star, that tries to find an accepting proof, but without querying the oracle on a complete tree that we can extract from, will eventually run out of transcripts, right? Eventually, it will have to query the oracle on an additional transcript that sort of induces a complete special soundness subtree from which we can extract. On the other hand, since we bounded the number of admissible challenges, now an honest prover also has a bounded number of transcripts that it can use. So the question is, can we set the parameters in a way such that an honest prover succeeds with high probability, but a malicious prover that tries not to induce a special soundness tree will not? So the answer is yes, if we have protocols up to a certain number of rounds. So sort of, I'll sort of skip the completeness analysis. I'll just tell you that the completeness here is bounded by lambda, or the completeness error is bounded by lambda times e to the minus 2 to the minus l times k, where k is the product of all the k parameters. This is kind of a straightforward analysis, so you'll have to trust me. But for knowledge soundness, now we want to argue that a malicious prover that tries not to induce a special soundness tree has much fewer attempts to find an accepting or a good transcript. So for that, we need to sort of introduce a combinatorial lemma that exactly bounds the number of leaves or the number of transcripts in a tree that is bounded. So its depth I is bounded by ki or ki plus 1, the arity. And in addition, this tree doesn't have a special soundness tree within it, right? Because otherwise we can extract and the prover failed. So this essentially bounds the number of trials that a malicious prover that tries not to induce a special soundness tree has in order to find a good transcript. So we bound this by this parameter phi. It's somewhat of an ugly expression. We don't have to parse it here. What I do want to tell you, and this kind of translates rather immediately into a bound on the knowledge soundness error of the compiler. What I do want to tell you is that we can actually set the parameters in a way that gives us good bounds both for knowledge soundness and for completeness. So the correctness error is what we said before. The knowledge soundness error, it turns out that it can be greatly simplified if you sort of set ki, the parameter ki, to be some c times ni, where it's the same c for all rounds. And then you can set the parameters in a way where the correctness error is 1/2, which is good because it's non-interactive. So if you fail, you can just resample the proof. And the soundness error is something like 2 to the minus lambda. The problem is that we set the parameters in a way such that the k's are a factor of r log lambda greater than the ni's. And sort of the tree that we get branches quite quickly, so we can only support log lambda over log lambda rounds. All right, so that's essentially what I want to say about this compiler. A fact that I ignored is sort of the following. So like Fishling's transformation, our transformation also relies on some notion of unique responses, which says that it's hard to find two responses for the same challenge. This is true for Sigma protocols, but most protocols that are multi-round do not satisfy the standard notion of unique responses. So we had to introduce a new notion, which is both sufficient for our transformation and is satisfied by most interactive multi-round protocols. All right, so I'll just conclude. We mentioned that we have these two transformations, each with its own advantages. Some open questions. So can you actually support up to log lambda rounds with our more efficient transformation or something that's equivalent to it? The second one is more general. It applies also to Sigma protocols, but all of these sort of transformations rely on parallel repetition. So is this inherent? This is kind of the big caveat of the transformations. And finally, can you prove our first transformation securing the QROM? This will require sort of new techniques or like the lifting theorem that we use to support other cases as well. All right, so with that, I'll conclude, and thank you.
We have time for maybe one very quick question. Okay, let's thank Leo and all the speakers in this session.